All right, let's look to summarize some of the things we've learned about projectile motion. So let's just look at the standard position equations first. And so let's look at the horizontal position as a function of time. So x equals v naught cosine theta t. Okay, and then y equals, we're going to go ahead and give it a possible initial height. So y naught plus v naught sine theta t minus 1/2 gt squared. There's not too many cases where we need a horizontal starting position, and there is no horizontal acceleration, so there's no 1/2 at squared. I went ahead and put a minus sign in because we know gravity always pulls down. If you take the derivative of this equation, as we've looked at in previous videos, right, dy dt, that is just the vertical velocity. The vertical velocity, if you took the derivative here, would just be v naught sine theta, right? That's just a number. Minus, and then if you did power rule, you bring the 2 down, the 2.5 would go away, and you're left with gt. But honestly, is this any different than what we said in a previous chapter where we define velocity and acceleration? I mean, it's the same thing. It's just we can't use any velocity, we have to use the vertical velocity, and then our acceleration is just negative g. And so this old school is just now this. This is the same thing we said in the last chapter. If we don't have any acceleration, the distance traveled is just the rate times time. It's just a horizontal rate, given the fact that we're looking for a horizontal position. If we look at it, and I'll look at this the general case of launching it from, this is, let's say y is a function of time. Let's start at a cliff height or a building, and we toss a water balloon off of it, and it does something like that. Okay, so the kind of key pieces here. One, this is what I would call the flight time. Might just call it TF, the final time or the flight time. This might be the time it's at a max height. And what you want to know, that at max height, right, we're looking at the maximum value there. That does correspond to a vertical velocity of 0. Now remember, not a velocity of 0, a vertical velocity of 0. The horizontal velocity the whole time is v naught cosine theta. There is no acceleration. There's no horizontal force, thus there's no horizontal acceleration. Horizontally, it's always going the same speed. But if you're interested in finding the time it's at a max height, which sometimes I would call, t max, you can just use this equation and set this equal to 0 and solve for t. How many seconds will it take for gravity to slow you down? Well, that's a pretty easy equation to solve. We can find t max. If we want to know t final, well, that corresponds to a y value of 0, right, when you're back to the ground. Well, when you get back to the ground, that's just setting this equaling to 0 and solving this quadratic. You can graph it and find the intercept, or you can just use the quadratic formula if you want. This is just a quadratic equation in which we are interested in the total flight time. Because if you know the total flight time, well, then you could figure out how far it went horizontally. Again, you have the position as a function of time. Once you know flight time, you could figure out how far it went. So what have we all kind of talked about here? Well, we can find t max, which allows us to find y max, or we can find this at the same time. We can just graph this and literally get this line and tell our calculator to find the maximum. It's going to be t max comma y max. We can solve for this 0 and find the flight time. So t flight. With flight time, we can find the maximum x value. We can find the horizontal position at any moment. What if I said, oh, there's something here that it flies over. There's a person laying on the ground watching you launch this, and they look up. When is it? Well, remember, if I'm giving you an x value, you can find the time. Once you know the time, you can figure out how high it is, or any of those things. All of these variables are related to each other. In a different video, I looked at relating x, y, theta, and v naught. You can do something like that. Again, this is not something that I would suggest memorizing, but I derived this in a different video. Y equals y naught plus x tan theta minus gx squared over 2v naught squared cosine theta squared. That's like the hitting the target one. I can tell you, You know, how fast you need to launch something at a certain angle to go a certain distance and be a certain height. And it's one of those things. It's just manipulating these equations. It's just solving this for time and getting rid of time. It's kind of like the no time equation. It's the equivalent of in 1D kinematics when you look at the v squared equation. We looked at that equation, and it's just an algebraic substitution into the standard position and velocity equation. Well, this is exactly the same thing. This is just for 2 dimensions, and so now we get an angle associated with it. We get an x and a y and a theta related to v, rather than just, you know, initial and final velocity related to 2ax. So it's very similar, and it's useful given certain things. Okay, so what else do we know about projectile motion? If it's symmetrical, there's lots of things we can do. If it's symmetrical, it's what I call a ground-to-ground launch. Then we know what? Well, we also can say that the Tmax, if we double it, we get T-flight. Nice symmetry, right? Going up, gravity takes away, and then gravity gives back. Gravity is what they would call a conservative force, meaning it doesn't steal any energy and not give it right back. Okay, friction would be an example of a non-conservative force. It takes energy away, and then it's just gone. It gets dissipated into heat. But gravity is going to take away energy and turn it to potential, and then it's going to give it right back to kinetic. And so what that means is, not only is the flight time double Tmax, but the initial velocity and the final velocity is the same. If you throw something at 30 meters per second at 60 degrees, when it lands, and again, that's with respect to the horizontal, when it lands, it's going to land at 30 meters per second at an angle of 60 degrees. Those angles are the same. Those speeds are the same in symmetrical cases only, not over here. Over here, it's going to be faster and it's going to be steeper. Hopefully you can imagine that if you launch something like this, if it has more time to accelerate in this vertical distance because of the building height, then it's going to be actually slanted more, and the length of the vector is going to be more as well. So there's all these things we can investigate, and again, there is a big difference between symmetrical cases. We even derive some, what I call sometimes the silly range equation, that v0 squared sine 2 theta over g is a range equation that only works in symmetrical cases. Again, we derived this of making some assumptions. I guess the main assumption we make here in this derivation is that the T-flight is just double Tmax. And again, hopefully that's obvious that it's true here and not true here, which means this equation does not work if you launch from a building. Okay, so you got your standard equations, you got some nice other ones. I mean, you can even use the v squared equation, you just use it in a vertical sense. I mean, let's say we are interested in y max. You could say at max height, the vertical velocity is 0. You just have to use the initial vertical velocity minus 2g, and we'll just say h being the max height. This is totally fine. This still works in one dimension, and this is strictly talking about the vertical dimension. Okay, these equations are nice. I wouldn't necessarily memorize them. Oh, you gotta go back in your notes. This is a squared. So if you copied that down and you're watching the video, sorry about that. That's definitely a v0 squared and then sine 2 theta all over g. Okay, so hopefully this is a decent summary of projectile motion. You should look at it. Hopefully you do some of the problems and you can, you see when, maybe this equation or this equation are useful. But, the standard kinematics equations in 2 dimensions are really all you need. And like I said, don't forget to use your calculator to solve some of these things. Sometimes it's just as easy to solve a quadratic by looking at the graph than it is by hand. Hopefully this helps.